Okay, in the last class, the last example was branching process, the Galton-Watson branching process. And I realized that I went through it a bit too fast, so I'm going to go through it once more. And actually, today I'll compute the transition probability for that. Okay, so before we start that, let me just tell you one thing, is that I had told you that the tentative method of evaluation would be, homework will have 60% weightage and final exam will have 40% weightage. And that's indeed final. So this is going to be the actual method of evaluation. So in particular, there'll be 6 homeworks total that you have to submit, out of which the worst score will be dropped. So essentially 5 homeworks per person will be evaluated, will be added to will contribute to the final grade. And each of these 5 homeworks will actually contribute 12%, making a total of 60% of all the 5 homeworks. And the final exam will have 40% weightage. Now, the only thing that we are not sure yet is the mode of the final exam. So at this point, it's not clear how the situation is going to be in December. So depending on the situation, we may actually have an in-class exam, in which case you all have to come to Bangalore. Or alternatively, we can have a Zoom-based exam, which is basically you will take the exam at your place, but we'll be invigilating it over Zoom. And finally, another option is a take-home exam. So take-home exam is essentially it's like a homework, but it's more extensive. So we'll see what we can do, and we'll take a decision later, and I'll let you know. Okay, so just quickly recall the definition of Markov chain. So it's basically a discrete parameter stochastic process taking values in a countable state space such that it has initial distribution A, so that's the distribution of X naught, and then it has transition probabilities P, which is this Pij's. And in this case, and this happens when the joint distribution of X naught to Xn is given by this product. Okay, and we have talked about it. We started with the Markov property, and then we came up with this definition last time. So this definition would imply that the future given the past and present will not depend on the past. So that would be future given the present. Okay, so this we have gone through, so I don't want to elaborate much on that. And the elements of S are called states. And so from now on, unless mentioned otherwise, a Markov chain will always mean a time homogeneous Markov chain. So this is something we decided last time itself. And the reason is that most of the theory of Markov chains is about time homogeneous Markov chains. And that's what we are going to present in this class, and that's why there won't be any time inhomogeneous Markov chain to be discussed, and therefore this would be our convention. Now recall that if you have 2 independent non-negative integer valued random variables, this is actually again recalling from last lecture also, with probability distributions A and B, then since these are independent, the distribution of X plus Y would be just the discrete convolution of A and B. Okay, this is what we went through last time. Now what can be checked easily is that this is a commutative and an associative operation on the set of all probability distributions on the non-negative integers. And of course, this commutativity and associativity is essentially coming from the commutativity or associativity of the plus operation among random variables. It's just borrowed from there. Now, for any probability distribution A, again on the non-negative integers, define the n-fold convolution A star n as follows. So A star n is A star A star up n times. So you basically convolute A n times. Of course, this is the case when n is a positive integer. When n is 0, we'll define this to be the delta 0 measure, the delta 0 probability. So this is the distribution. So this is the Dirac probability distribution, which puts mass 1 at 0. And we also discuss why this is the case. So this is the case because this acts as the identity element for the star operation. More precisely, in this case, if B is delta 0, in other words, if Y takes the value 0 with probability 1, then X plus Y will have the same distribution as X, and therefore X plus Y will have the distribution A, and therefore that will prove that A star delta 0 is A. Therefore, delta 0 is the identity element for the star operation, and that is the rationale behind defining A star 0 to be delta 0. By the way, in the last slide, there was some typo. I'll actually correct it and upload the typo, but instead of writing bold A here, I wrote normal A. But it's okay. I mean, I think it was obvious. That's why nobody really bothered to point that out. But I'll make that correction and upload it. But I won't send an announcement about it. It's obvious, I think. Okay, now the point is, what is A star n? For any non-negative integer n, so what is A star n? So essentially, if you have a sequence of random variables, say y1, y2, and so on, which are IID and follows the distribution A, then y1 plus y2 up to yn, this random variable has distribution A star n for any non-negative integer n. Obviously, for a positive integer, you're just adding n many independent random variables, each of them following the distribution A. Therefore, from this fact from the previous slide, an induction on n, you get that summation of yk, k running from 1 to n, does follow the distribution A star n. On the other hand, if n is 0, then by convention, this is a sum from 1 to 0, then by convention, this is 0. This is a random variable 0, and therefore, that also goes well with this convention. Okay, we'll be needing this today in the calculation. That's why I stressed on that.